Let's answer a question on standing waves. Part A we've seen before. Choose your favorite difference and write it down. Part B. A loudspeaker connected to a signal generator is placed in front of an open end of a tube. So a signal generator creates an electrical signal, and then the loudspeaker turns it into a sound. Right, so the sound is being produced. We can imagine what's going to happen. The wave is sent down. It reflects back. And now we have two identical waves traveling in opposite directions. So this can produce a standing wave. We have the conditions. Let's read on. The frequency of the sound is increased from 0. At 92 hertz, the first large increase in intensity is heard. So if it's if it's reaching high intensity, that means a standing wave must have formed. And because this is the first time that happens, this is the first frequency, or the first harmonic. On the diagram above, draw a representation of the wave, and they really mean the displacement of particles for 92 hertz. Okay then, this is the first standing wave we can produce. We know that this has to be a node. Particles against this wall cannot move left or right. This has to be an antinode. The particles here, they reach maximum displacement. They move really far to the right and really far to the left. So our standing wave goes from node here to antinode, and that's the first one that we produce. So we stretch that shape across the pipe. And then we can draw a dotted line to show the other half of the oscillation. Not only do the particles reach positive displacement like this, they also reach negative displacement. They move to the right, positive, and they move to the left, negative. The length of the tube is 0.91. Determine the speed of sound. Speed, we know, is f frequency times lambda. We know f1, so we need lambda 1 to calculate the speed. How do we find lambda 1? We can look at the picture up here, and we could just realize that the length L fits 1/4 of a cycle, or in terms of distance, it fits lambda over 4. That's lambda 1 because it's the first wave that we can produce. Or if you don't want to do that, you can memorize the equation n lambda n equals 4L. That's the equation for a pipe that has one closed end and one open end. When we're at the first wavelength, that's lambda 1. We put a 1 for n, and we get the same thing that we wrote here. Lambda 1 equals 4L. And so if we calculate, the length is 0.91. And this gives, it's going to be 3.64. Next, we calculate the speed. We take the frequency of 92 hertz is the same as 1 over a second. And then we have 3.64 meters. And how many meters per second big is this? It's 334.88 meters per second, which is going to round to, we've got 3 sig figs here, 345. The frequency is increased above 92, so you keep increasing the frequency. Calculate the frequency at which the next large increase is heard. Well, we know that in a pipe open at both ends, open at just one end, this is the first wave we can fit, and this is the second wave we can fit. And how much did we increase the frequency? We haven't doubled the frequency here. If we doubled the frequency, we would have something like this, and you cannot produce that shape in a pipe that is open at one end. You have to have an antinode, and so this shape does not fit. So you have to skip the second harmonic and jump straight to the third harmonic. So F3 is equal to 3 times F1 or 3 times 92, which gives 276 hertz.